All right, so where are we? We're doing these loop invariant algorithms, right? Where you have a loop invariant and you establish it and you maintain it and you get the postcondition. All right, so now we're doing another easy example, slightly harder. We're ramping ourselves up. All right, now we're going to do insertion sort. All right, and this just says, just because you know insertion sort, don't go to sleep, because you know what I'm teaching you now is not insertion sort, but it's just making sure we got loop invariants down, right? So code, right? You can look at code, and I personally don't like looking at code, right? I mean, you have to really struggle to get what that means. So we're going to instead be doing this. We're going to do these steps. Do you remember the steps? Should I review them? Right? You should have these memorized now, right? What's the precondition and the postcondition of the problem? I'm going to give you those. What's the loop invariant? What's the picture true at the top of the loop? What's our measure of progress? When the loop invariant's true, how do we take a step? That's the action, right? And if you're here for the tutorial, we spent a long time looking at how to think about this action as an action, but also as a math statement relating the old values to the new values. Actually, this is reminding me something. I kind of like that, and so when I went home, I made PowerPoint slides about this. So would people like to cover the PowerPoint slides on that, even though we did it in the tutorial? Yeah? All right. It'll only take a few minutes. So we'll do that now. All right? So that's this step. Right? And then there's the when do you stop? Proving that you maintain the loop invariant. Proving that you make progress. Proving that you can establish the loop invariant. Proving that you don't have infinite measure of progress at the beginning. Measure of progress goes to 0, you'll exit. Getting the postcondition. Everybody got those? So let's jump out of these and go F5, prove physics using loop invariance. Is it here? Oh, no. Is it here? Using loop invariance. I don't see it here. Code. Oh! Code from loop invariance? What's that? No, that's not it. Nope. I made the slides, but evidently I didn't upload them. So we can, if you want to see them, we can see them next class. All right? Because I don't think it's not there. It's not there. All right, so let's go back to this. Hello? There we go. I don't know why you're so slow here. Okay. All right, so now let's kind of imagine we're in a test. And I give you a new problem you've never seen before, which of course isn't this, because you have seen this before. And what's the precondition is that we have a bunch of numbers, right? And the picture here says it's a bunch, right? And here, what's the postcondition is that those numbers, we have the same numbers with the same number of repeats, and they're sorted. All right, everybody good? Pre-post condition? So we got to think, where might we be during this computation? Right? Where might we be? Well, maybe at some point we will know some weird collection of facts. Right? And how are we going to represent this weird collection of facts? And how are we going to use it? How are we going to write a loop invariant about it? Does this seem useful? you hope to say, this doesn't feel useful, right? This is a weird collection of facts. This is where I'm kind of up a tree. I have a bunch of things that I just don't understand, right? So instead, we're going to kind of a loop invariant, which seems reasonable. Hopefully everybody can think about a loop invariant, right? Here are a bunch of numbers. Here they're all sorted. What's going to be true in the middle? Some are sorted. Some are sorted. It's as hard as that. Right? It's hard as that. So, how are we going to say it? We're going to say some of the numbers are sorted. The rest of the numbers are not sorted. Right? Everybody good? That's our loop invariant. And, maybe the picture isn't quite good enough. Maybe you need to write it out in English. Some of the numbers are over here. They're sorted. Some of the numbers are not sorted. Right? The rest of the numbers aren't sorted. Right? You can write it out. Right? And now, here, it's a windy day. We don't really know where we are, right? So one thing we don't know how many numbers are sorted, right? And this is kind of implying we don't know which numbers are sorted, right? Now, given a specific piece of code, a specific implementation, maybe it would be specified which ones were sorted, right? But here, I'm trying to keep it open as general as possible. What's the advantage of that? One, it shows you that it's a nugget of why does this algorithm work? Is it based on which numbers I'm sorting? Right? It helps you understand deeper, but also it gives that more power to the implementer. Right? Somebody else is going to have to code this up. I'm giving the implementer the power of which numbers. All right? So we fly in from Mars, and we know that something is true, right? So what's our measure of progress?
The numbers on the right-hand side continuously get lower, so that you have more sorted numbers on the left than you have on the right.
I didn't like the word continues. What's wrong with the word continues? It feels action-y to me, right? And we're now, remember what a measure of progress is. It takes the state of the computer and maps it to one real number, right? And now, of course, we're at some point going to prove what you're trying to say. Well, this measure of progress is going to change, which direction we want it to change, right? But when we're just defining the measure, right, we want to say, well, it's either the number of numbers not sorted or it's the number of numbers sorted, depending on whether you want it to go up or down. Right? And we're generally talking about them coming down, right? So we could talk about the number of numbers not sorted, right? But I could have easily started this whole course with them going up, right? I don't know why that happened, right? The number of elements, right? So now we have to define a step, right? We're here. We don't know how we got here. What is our action going to be? Right. We take some number over here. I don't care which one. We find out where it goes, right? And we put it there.
Sorry, Professor, I'm still a bit confused. What exactly did you define as a loop invariant?
Loop invariant is some of the numbers are sorted, and the rest of the numbers are not sorted.
Okay.
Right? So here, you have to kind of argue that we've maintained the loop invariant. Would you agree that if some of the numbers are here and some are not here, these are sorted, the rest are here? So what are the two issues? We have to show, one thing we have to, maybe that's not stated more clearly, if we were really being formal, in the loop invariant, we'd want to add every number somewhere, right? Every number is only there once. Now you might say, well, there might be repeat numbers, but then those are if there are 2 3s, then those 2 3s are there and only there once, right? So one thing that we need to make sure is that that's maintained, right? And that's maintained because we're taking some number and we're moving it, right? So we haven't created or destroyed any numbers. We have the same collection of numbers. And we have to maintain that these numbers are sorted, right? And they were sorted, and we inserted a number in the right order, so they're still sorted, Right? Does that make sense? Right? And then, are we making progress? Now what you're saying, oh, look at, we're making progress because the number of numbers over here is going down. Right? And then we have to look at the other things. How do you establish the loop invariant? Well, you could establish it by taking one number and putting it by itself, right? But here I'm choosing to say this is a perfectly good loop invariant, right? A perfectly good example of our loop invariant, right? Some number of numbers is sorted, right? What number is that? It's 0. 0 is a good number. The rest of the numbers are over here, right? So to go from here to here, all I have to do is kind of set up this data structure, right? Now we have this empty list. And then we keep taking steps. And, initially, how much progress do we have? Well, it's the number of numbers here, right? It's not too much. And when this list comes down, we're going to have what's our exit condition is when the number of numbers over here is 0, right? So we'll exit. Now what do we know? We know that the loop invariant's true, and we're doing this one here, right? The loop invariant's true, and the exit condition's true, so we're going to try to get the post condition. And the loop invariant says some of the numbers, right, are over here not sorted, but that number is 0. So all of the numbers are over here sorted. So this is what loop invariant plus X condition gives us. And what do we have to do to get down here? We have to just delete this. Right? Everybody good with that?
So loop invariant is like a very general statement about what's true at the top of the loop.
Yeah.
Which is why we say like some numbers are sorted and others yeah.
Yeah. Right, so it's a picture that tells you something, but it doesn't tell you everything.
Yeah.
Doesn't tell you which numbers are sorted or how many numbers are sorted. And I have slides later which saying what we want it to do. One thing we want the loop invariant to do is to move gracefully from the precondition to the postcondition. And what do I mean by gracefully is here the loop invariant is pretty much exactly the precondition, right? And here, the loop invariant is pretty much exactly the postcondition. And what did we do in between? We moved gracefully, right? You know what I mean? It was just small steps. Yeah?
For the loop, invariant is some that are sorted and some are unsorted.
Yeah.
But like the pre and post, there is an empty loop box, whatever. But is that still true? Because some is unsorted?
Yeah. Yeah, one of the things that I've sort of said a few times, and I'm going to keep saying, is that, oh no, it's okay to answer your question. I'm just saying I'm linking it to a more general topic, right? Your question is good, and the more general topic that I think it's linked to is that the empty set and the empty tree and the empty number, I mean, these are all good numbers, right? 0 is a perfectly good number, right? So when I say that the loop invariant says that some numbers are sorted, then 0 is a good number, right? I mean, do you have anything against 0? No. Right? I mean, he thought that was funny. Sometimes I tell jokes that people think they're funny, right? All right, good. So here I'm saying the loop invariant's true because some numbers are sorted. It just happens to be 0. Does that answer your question? Yeah? Everybody good?
With the loop invariant we chose, it would apply to like other sorting algorithms already.
We're going to get to other sorting algorithms, and they're different. So I'm going to go no. All right, so now let's do running time, right? So you remember somebody asked, do we have to do the whole measure of progress thing in order to prove that it halts? And I at one point said no, but then I said yes. And the yes is there's going to be a question about what the running time of the algorithm is, right? And so here we have to think, well, our initial measure of progress is n. Every iteration, our measure of progress goes down by at least 1. And we stop when the measure of progress is 0. Hence, how many iterations are there? N, right? Pretty straightforward. But then we have to ask, okay, that's great, but what's the running time of each iteration? That might not be 1, right? So what's a classic iteration is we're inserting a number here. And so we have to think about the running time of inserting that. And, you know, if you're me, you're going to say, oh, I can do binary search to find out where it goes, right? And so that's only log time. But does that work? So if I find out where it goes is here, then what do I have to do? I got to get it in there, right? So I have to think about what data structure I have here. The data structure is an array. How do I get it in there? It's got to shift everybody, right? So that's going to take, you know, about the length of this list here. Now you might say, well, I could instead do a linked list. If I do a linked list, what's the problem?
You just traverse through the list.
I can't do binary search, right? I have to walk down the list, right? What is another data structure I could use here? I could use some sort of tree, right? A tree, you know, an AVL tree, or I could use a heap. I could use some sort of tree, and then I could get it down to log n, and then our running time wouldn't be n squared, it would be n log n, right? But right now, let's just assume but then we would be doing heap sort instead of insertion sort. So assume this is an array, in which case, when the list is of size I, it takes me I time to put it in there, right? And so my running time is 1 plus 2 plus 3 plus 4 up to n. Everybody see that? And you might remember that one of the topics that we were supposed to cover in the math section was how to add things. And this is why you need to add things, right? Everybody know what this, anybody know what this adds up to?
N plus 1 over 2.
Yes. In fact, Gauss is supposed to have said, you know, he was in kindergarten, and his teacher was trying to punish him by adding up the numbers 1 through 100, and he did this and pissed her off even further, right? So we're trying to add 1 to 100, right? Here, 1 to 100, whatever it is. What we can do, what Gauss did in kindergarten is he switched the list around, and then he added this way. So here we switched the list around, and we put them together. Where are we putting them? There we go. We got them together. It's supposed to come together gracefully. There we go. Right? And so we got n times n plus 1, but it's only half of them, right? So divided by 2. Right? Everybody got that? Now, one thing I always think funny about how people teach this stuff is they'll have a big section on big O notation, right, that we don't care about the constant in front, and then they have a big section on how to give answers like this, and I don't care about the 2. I certainly don't care about the plus 1, right? I want to know that this is big O of n squared, right? So we're not going to spend too much time on this, but know that in my past I would have forced you to spend a lot of time on this. Let's just get a vibe of it, right? Here it's saying I'm trying to add up the sum of f1 plus f2 plus f3, right, up to fn, and the function looks something like this, right? And this says if the function is arithmetic-like, it's a polynomial, right? This basically says this thing here goes away. If it's not an exponential, right, then it looks kind of like a polynomial. And then what's true is, well, we're adding up all these terms, and about half of the terms are all up within a constant of each other. Then the answer is that the sum is more or less within a constant the biggest number times the number of numbers going. All right, so here, this is just what I said again. And so we're done. Everybody good? All right, so, sometimes, actually people don't ask this anymore. When I first started teaching, everybody wanted me to run through an example, which I always thought was dumb, and so was a little sarcastic about it. So here's me being sarcastic. All right? Catch this sarcasm in these slides. Here we're going to implement it. Right? So we insert a number, and then we insert a number, and we insert a number. We do it. There, we did it. All right, everybody got that? Did it make you happier? All right, so, now it's the post condition. We did that. All right, so everybody got that algorithm? All right, so here it is.
So, like, you know, like the document that you made where you talk about like your steps.
Yep.
There's different steps that you do for like defining loop invariant. So would this fall under like more of the input, more of the output, narrative?
You're getting way ahead. We're going to have those later today.
Okay.
And you should know which it is. It's more of the input, but we'll get there. All right. So here, at some point I wrote this. Probably when I first started teaching here, right? So here, if I was standing on a subway chatting, I can imagine saying this, right? So let's kind of read it. I'm trying to tell you insertion sort. I might say, well, how do we do insertion sort? We maintain a subset of the elements sorted within a list, right? The remaining elements are off to the side somewhere. Okay, great. What did I just do there? I defined the loop invariant, right? I started by saying, hey, I'm telling you this algorithm. What's my loop invariant going to be? And then I start talking some more. Then I say, well, initially think of the first element of the array as a sorted list of length 1. What did I just do there? Precondition to the loop invariant, right? The precondition is I have this array, right? And precondition is I have a bunch of numbers, and I'm establishing the loop invariant by saying I have a sublist of length 1 that's sorted, right? And now I'm going to say, one at a time, we take the elements that are off to the side, right? We say their numbers off to the side. I take them one at a time, and I insert them into the sorted list where they belong, right? And right, so that is my action, right? That's my action. Take a number, sort it where it belongs. Then I say, this gives a sorted list that's one element longer than it was before. I did two things there. I kind of hinted at the loop invariant being maintained, and I hinted at the fact that progress was being made, right? And then I'd say, when the last element has been inserted, what's that? That's my exit condition, right? Then the array is completely sorted. That gives me the post condition, right? Does that make sense? Can you imagine saying that on the subway? Right? Depends on who you're talking to, of course, right? Now, one thing I want to add in here is what I don't like about this as an answer is just take it and break it into paragraphs and tell me what you're doing in each paragraph, right? Otherwise, this is a perfect answer for an exam question, assuming that you broke it in paragraphs so I could find the pieces, right? Everybody good?